Hey, Mr. Klein here to teach lesson 33, the last lesson of the unit, which is going to be about independence once again. So you should be right here. And in fact, the first page of the lesson is a review, and we're going to skip that. So I want you to turn to this page. I'm going to give you an example of independence, and then I'm going to give you an example of dependence. Recall that two events, A and B, are independent of each other if and only if B occurring has no effect on whether A occurs. So let me give you an example of two events that should be independent. First is A, the event that a student gets an A on a quiz, and B, the event that a student rides a bike. These things don't have anything to do with each other, so they should be independent. Now let me show you a way that we can test for independence. Let's start by finding the probability of A. With a Venn diagram over here, we can see that A is these two regions of the Venn diagram, and if we add those two regions together, we find that 80% of students got an A on the quiz. Pretty good. Now, let's do this. Let's see if B changes A. Let's find the probability that A happens given that B happened. Recall that this right here means given. So if we are given that B happens, that means that we are only looking at the B circle. So we're only looking at these two numbers, which means that the denominator of our fraction is going to be this plus this. 20% plus 5% gives us 25%. Now in the numerator is going to be the part of this circle that is in A, and that would just be this part. So our numerator is going to be 0.2. If you take 0.2 and you divide it by 0.25, lo and behold, guess what you get? 0.8. Now think about what this means. This means that the probability of A is 80%. If we know that someone rides a bike, the probability that they get an A is still 80%. That's what it means to be independent. These are the same. Now, let me give you an example of two dependent events. Let's suppose once again that A is the event that a student gets an A on the quiz, but this time B is the event that the student takes the test blindfolded. These we think should be dependent. Specifically, a student that takes the test blindfolded should be less likely to get an A. So the probability that a student got an A on this test is this region and this region, so it's 80%. I kept it the same as the last problem. The probability that a student gets an A, given that they took the test blindfolded, means that we need to look just at the blindfolded region right here. If we add these two numbers together, we get a denominator of 0.25. This time our numerator is going to be just the part of this circle that got an A. And the only ones that got an A are right here. So that would be 0.1. If you divide 0.1 by 0.25, you get 40%. Translation, if you know that a student took the test blindfolded, the likelihood that he or she got an A is going to go down. So in sum, here's what I want you to get out of this. We have an independence rule, and the independence rule goes like this. A and B are independent IFF if and only if the probability that A happens given that B happens is the same as the probability of A. This statement is basically like saying B happening doesn't change the likelihood that A happens. All right, go to the next video.